Alright, so in this video, I want to give a short introduction to secant lines and tangent lines, and then also a quick introduction to kind of the big picture focus of differential calculus. Alright, so what I've got here is an x and a y plane, and I've labeled the x-axis with time and the y-axis with displacement. And so we have an object that's moving and we're tracking its displacement over time, or relative to time. And what I'd like you to think about is, how would we figure out the average speed or the average rate of change from, let's say, maybe 6 seconds over to 12 seconds. If we wanted to know what the average speed was there, we would take the distance at 6 seconds, we would take the distance at 12 seconds, we would figure out the difference in time, which is 6, right? And then we could figure out what the average speed was. Not a hard problem, you've probably been doing it for years, okay? What that amounts to being, though, is the slope of this line, which is called a secant line. Okay, so that blue line is called a secant line. A secant line is a line that hits the graph at 2 or more points, but really 2 points that we're worried about analyzing. And what I mean by that is this line is clearly going to hit this graph at other places, but at least 2 points, all right? That's in contrast to a tangent line, which hits at 1 point. So let me show you what the tangent line would look like right here. This would be a line that hits 1 point in an area, and that's called a tangent line. Okay, so we've got tangent line and a secant line. Let's go back to our average speed question here real quick. So again, figuring out the average speed is not a super tricky problem, I don't think. But what if I wanted to know how fast the object is going at 8 seconds? At exactly 8 seconds. So here in this situation, I don't have the luxury of a time frame. So I can't just take a distance in time at one spot, a distance in time at another, and find the slope of the secant line. There is no secant line. Or you can think about, if you're shrinking the secant line, the secant line would disappear, right? And so that's actually a fairly difficult question. What is the instantaneous speed at 8 seconds? Clearly the object has speed, right? If you were to put a wall in front of the object right at 8 seconds, it would hit it and there would be physical ramifications for this object smashing into the wall, right? So clearly it has speed, but also no time has elapsed. So it's like, well, how do we understand what the speed of the object is at a given instant? And that problem right there sums up a lot of what we'll be trying to figure out in differential calculus. We'll be talking about instantaneous speeds, instantaneous rates of change in all kinds of different contexts, and what they mean, and hopefully we'll be tuning sort of your intuition about what's going on there as well, using the mathematics to kind of support it and guide you. So that's where we'll be kind of headed with differential calculus. And that's also just a quick refresher on the difference between a tangent line and a secant line. Right, and then following this is going to be a quick video clip on average rate of change as well. So, all right, I just also wanted to quickly add into this video a quick note about average rate of change, just so we're all on the same page on what that means. So the average rate of change the easiest way to define the average rate of change is, well, the average rate at which a function changes over a given interval. And the way that we find that is finding the slope of the secant line that connects the 2 points. So for instance, if in this first example, or the only example actually, if we had the function f of x equals x cubed minus x, and we wanted to know what is the average rate of change over the interval from 1 to 3. What we would do, you don't really need to sketch it once you've done enough of these, but we can sketch what the function sort of looks like. It's got an intercept at -1. It's got an intercept at 1. And it does something kind of, oops, it also has 1 at 0. So, real good drawing here, Cresswell. So it goes up, down, and something like this. Okay, actually, let's say it does this. Okay, so let's put 1 here, obviously, and then let's put 3 out here. And you want to know what the average rate of change is. So the rate of change, instantaneous rate of change is actually sort of difficult to figure out. But if we want to know what the average rate of change is from here to here, we just find the slope of that secant line. Okay, and so to find the slope of that line, we just need to take y1 or y2 minus y1 divided by x2 minus x1, or the way that I like to write it, because it uses function notation, is if we call this point f of a and this, if we call this point a and this, if we call this value a and this value b right here, so this is a and this is b, then we can write this for the average rate of change, which is f of b minus f of a divided by b minus a. So there's your average rate of change. That's the slope of the secant line over those, over that interval. Okay, so the average rate of change, and again, just think of this as like how fast is the function changing over that interval. So the average rate of change then for this one would be f of 3 minus f of 1 divided by 3 minus 1. You end up with 24 minus 0 over 2, so you get 12. Okay, so the average rate of change there is 12. And you've seen this before, I'm sure, in Algebra 2 and Pre-Calc, so I don't want to say too much about it, but I want to make sure that it was on your radar. And that is also to say that this equation right here is very, very, very important. It will not go away, okay? So that is something that is cardstock worthy. That is something that you might want to memorize eventually, especially as it comes closer to the AP test. That is the average rate of change of a function over a given interval.